My name is Ashley Woodcock.
I'm Bea Williams.
I'm Elijah Santantini.
I'm Dominic Scialzo.
And Stephen Burkhart.
Josh McKeel.
So our goal is to make an attraction for visitors and future students to view, and this will be able to demonstrate students' hands-on capabilities. Our purpose is to help market Alfred State and attract new students to come here. The ideal lifespan is going to be 5 to 10 years.
Okay, so first thing we kind of started working on last semester in the fall was track, mostly because it's a very fundamental aspect of our whole project. And coming with that, there's a few major design criteria that we had to choose from. Cool. Two major design criteria we had to do was the form of actual wire. We chose a 4-wire system, 2 wires on the bottom for the marble to sit on, 2 wires on the side for support. We chose 9-gauge galvanized steel wire. I'll get to that in a second. And the other major design criteria we had to choose from was how to actually retain the track together, how to hold it together. Most wire-based tracks tend to be welded, at least from our research and reference models, but what we chose was 3D printed clips we designed ourselves. 3 major reasons for that. First, they're very cheap to produce, very producible. We can just print 20 of them at a time, and they're, compared to something like welding, they're relatively low skill. So there's less skills we need to acquire, and more people that can help with assembling the wire. So track jigs. First, you can see right here is the straightening jig, where we take the big coil of wire and make it straight. To the right, you can see the bending jig, which is how we take the straight wire and bend it into predictable sizes. And that sort of brings us into track material science. First off, we chose the galvanized steel wire, one, because it is soft enough to bend by hand, while still being rigid enough to hold itself together. And another thing being it is relatively cost effective. We bought it in 1,000-foot rolls as fencing wire for about 10 cents per foot. And that was a major contributor. Here you can see the spring back function that we acquired experimentally. Basically, when you bend a wire to a known radius, it'll spring back to a larger radius. Springs back, and then you line it up with one of the major and minor divisions, and it'll tell you how many degrees you've actually bent. And then we can move on to.
So for our frame, it is a 6x5 by 6 foot frame, and we chose this based on the door frames, getting it from inside this building to SLC and seeing as far as, or as big as we can possibly go. And so we also did a cost analysis between 2 different companies to see, and their bars to see what we would be able to spend the least amount of money on. And in order to do that, we also wanted to repurpose old bars and different fasteners. We also wanted to keep the dust outside of our machine, so we created walls and floorings and roofs. And so that, and we did this by going into the makerspace, which is upstairs, and we started using a planer saw, bandsaw, and jigsaw.
Alright, so next is the track support. So with the frame and the tracks, we needed some way to actually mount the tracks and support them so that they don't just fall and wiggle around. So we did this with copper pipes and 3D printed brackets and pieces that will interface with the aluminum, extruded aluminum on one side and the tracks on the other, following a similar clip profile. You can see we've got the kind of original concept design, and after some iterations we landed on this. There's the base kind of type of support is just sticks straight out, which is nice for the shorter ones, but then we can pretty easily add a brace to keep it square for our longer supports. Then we also have a variation for a vertical support that hangs down on the ceiling for some of the higher up tracks. One of the first problems we encountered with the whole marble machine question is how are we getting the balls from the bottom of the machine back up to the top? So our lifting mechanism is based on a corkscrew that sits inside of a square acrylic tube. And essentially the balls roll in at the bottom here, and get pushed up into the corner of the tube. And since they have nowhere else to go, they can't roll back down since it's a square. They will get pushed up and eventually pop out at the top of the lift with this special piece right here that kind of acts like a cam. And the whole thing is, it's a 1/2-inch keyed metal shaft with 3D printed each of these sections. This is about 2.5 inches tall. They just slid down over the shaft. It's held in by bearings and belt driven by an 110 volt AC motor.
Okay, so the marble machine being a kinematic sculpture, we needed sort of visual flares for the marbles to do something interesting to look at. The first one is the marble splitter, one of the more functional ones. We needed a way to have one constant stream of marble split into multiple ways. You can see we have this 4-way and a 2-way. Quickly go through them. This is another one that's a spiral, just a very cool thing to see the marbles whip around in. Funnel. This also sort of acts as a track recombiner, so it can combine 4 tracks together into one. It was kind of based off of those penny coin hyperbolic funnels you'd see in old shopping malls and stuff. And finally, we have Plinko, where you put a ball in the top, hits a bunch of pins, ends up in different spots. We sort of turned the Alfred State logo into a large Plinko. Unfortunately, we couldn't have it for this demonstration because of the back panel, but it'll be installed shortly. That should be it for mechanisms.
So for a big part of what we wanted to decide to put into our marble machine, we wanted to make sure that we included iconic moments from Alfred State. That was our big idea. So a lot of the things that we chose were really important to student life on campus, but also the school culture. And we didn't base this off just what our personal choices were, but what the school itself highlights through advertisements, stuff like that. So 3 of our main landmarks that we decided to do are the Bell Tower, University Police, and Pioneer Stadium Field. So the reason why we decided to choose the Bell Tower is because it's one of the main features that I use during marketing or advertisement for Alfred State. Its iconic ringing every 30 minutes is something that's also usually mentioned when walking past during admission tours for potential new future pioneers. The Alfred State Field not only holds most of our athletic meets or games, such as for the men's and women's soccer, track and field, and football, but it also holds iconic moments for students, such as incoming student, the formation of the A that we do during the week of welcome. That's one of the first moments that students do when they come on campus, as well as graduation, which is their last. And then finally, we have University Police, and it's not only important to acknowledge the workforce that protects both the college and students, but also the village as a whole, 24/7, all days of the year, but it's also got a historic moment for both the school as well as the town. It's one of the first Greek life houses. It's originally Theta Gamma's house. It was founded in 1912, and it's the first fraternity that was founded at Alfred State. One of the next parts was finalizing the machine design. So after we started getting all our final prototyping and modeling for the landmarks and everything, our next move was to put it all together into a 3D model assembly. So basically what we did was, as we were all used to using different things such as SolidWorks or Inventor, we decided to use an online software that called Onshape, which is essentially the same thing as they all usually are. But this one allows you to work online together, so you can work on parts and assemblies at the same time. So that means multiple of us could be in the assembly putting things together, even if we were at home or in different places. And this also allowed us to upload files from different places, so like a SolidWorks file or Inventor file could all be uploaded onto Onshape and be uploaded into the assembly with no issues or minimal issues with conversion, which got rid of most of our problems that we were facing in regards to the communication about that. This finalizing the machine design also allowed us to have measurements for finalized placements such as the bell tower, the funnel, as well as most of the track design and the way that we wanted it to lay out within the machine.
All right, so we have 5 major computer and electrical systems in the machine that we integrated. Those are the backlighting for the Alfred State Plinko and lettering. We have the speaker system because we wanted to incorporate, as you see we have the bell tower, we also wanted to incorporate some of the iconic sounds of Alfred State. So every hour and a half hour, those speakers chime out with actual recordings of the bell tower. We're also implementing an LED rail, which is a translucent plastic tube that sits around one of the tracks. And then there's a sensor at the beginning of that. When a marble rolls through, it's trailed by an LED light. And then we have the marble counter display you can see on the right-hand side of the machine. That's tracking marbles with a break beam sensor. It'll count up on the screen. And then also during the off hours of the machine, it'll display a little sleeping animation. Then lastly, we have the marble lift, which is controlled by the pie. So in order to increase the lifespan of the machine, we thought it'd be a good idea to have hours when the motor was not running. So the on hours are 7 a.m. to 11 p.m. When it's not during those hours, the motor will not be running, so we're hoping to increase the lifespan that way. Then when it came to the actual assembly of the electrical components, there's kind of a hodgepodge of components. We've got our 5-volt power supply for all the DC power components. We have our motor controller, our amp, the Raspberry Pi, Arduino's, real-time clock modules to keep track of the time for the bell tower sounds. And then from that, since there's so many different components, I had to model and print a bunch of brackets to actually mount them to the steel plates. So there's a lot of design in doing that. Then once those get attached to the plate, that's then mounted under the machine and then hidden under the floor, tucked away. And last, I'd like to talk about the machine startup. So it's a fully automated startup. All you have to do is take the power cord, plug it into the wall, it boots up and starts running. This is controlled from the Raspberry Pi, so once that receives power, there's programs on it for the speakers and the display that automatically start up. It's also waiting for a signal about the time from the Arduino. If it's during the on hours, it'll get a signal that tells it to turn the motor on. If not, the motor stays off and won't turn on until 7 a.m. the next morning.
Yeah, so manufacturing. For our manufacturing, we chose 3 main methods. Laser cutting for things like the back, Alfred State, the Plinko. 3D printing was our other main one. We chose that for its versatility, its speed, its many different materials. Including in this project, we used PLA, PETG, ABS, and then some different colors and material variations. For example, the bells that are being printed out right now are sort of a metallic bronze. We also chose 3D printers because it gave us the most volume over time. Next slide. We'll get there. We have 6 of our personal 3D printers and then 2 school printers as well. So we created somewhat of a 3D printing farm right next to our machine. The reason why is because we wanted to have a workflow that could be as fast as possible. So when our printers are 10 feet away from a machine, we can design something, print it out, and then work on the machine right there. For example, with how many tracks and how many track clips we have, if we're working on that and we run out of clips, we just walk over, grab more clips off the machine, press reprint, walk back over to the machine, and we're going again with no downtime. That process flow has really enabled us to work on this as fast as possible. As well as that, with 3D printing, we used a special type of 3D printing called multicolor, utilizing an AMS, an automatic material system, with Bamboo Labs X1 Carbon. This one in specific has 4 different colors that it can print from. It essentially slices the layers in the G-code so that each one is a different material. And when it comes time to it, the automatic material system cuts off the old PLA, inserts the new PLA, and then prints with a new color. Specifically, we use it for the field. That is 8 pieces that are interlocked together, each containing 4 different colors. And then there are 5 colors. The light blue pieces are inserts into it as well.
So a really important piece of our project was documentation. So especially at the beginning, some most big parts of our documentation included our charter, communication plan, and our Gantt chart. So our charter included stuff like our project goal and summary, goals for each semester, as well as our inclusive and exclusive scopes for the project. For our goal for the end of the fall 2024 semester, we were able to achieve that by having all the material on campus or ordered ready for us to be able to go and start building at the start of the spring 25 semester. And we are currently still confident that we'll be able to have the machine fully up and running by the end of exam week, which will mean that we will have hit our spring 25 goal of completing the machine and having it installed down in the SLC. For our communication plan, it was basically just communicate as openly as possible towards each other, so update each other in our teams, continuously update documents on our OneDrive, and ensuring that everyone was clear on where you're up to in our tasks. And then our Gantt chart was probably our most important document for us. It included, we broke it down to 3 sections. One was initiation, which was the actual creating of the document, as well as setting up our group and roles. Our third one was planning, which included a lot of the 3D modeling and prototyping, as well as planning long-term goals such as how we were going to move the frame, which included the measuring of the doors that we discussed earlier. And then the final section was execution. So this was the actual like the track assembly, installation, finalizing 3D prints of models and everything, and then it will be finally installed in the SLC. So our Gantt chart includes who the role is assigned to, the date it was assigned, and when we would like it completed / when it was completed. And then each member could go in individually and update how far along they are on their task. Next we have our budget. So we had 3 streams of budget coming in for us. We applied for the Applied Learning Fund at the start of the fall semester, which gave us $1,500. We also have the Recruitment and Retention Fund, which was another $1,500 for us. And then we were very lucky to be able to get a donation from Greg Simmons, who allowed us to have an extra $3,000 on our budget. So we ended up starting with a $5,000 budget for our marble machine. You can see by at the end of the fall 24 semester, this was just after having a few of the frame ordered and a few of the 3D filaments ordered. We had $2,300 left, and now currently, as we stand, we have $280.63. For our inspiration for the machine, we used Creative Machine, and it was one of our biggest inspirations for this project. They have a lot of access about how they do certain things, the inspiration of their builds and everything, and it made it really easy for, or it helped us be able to apply the ideas that we wanted with Alfred State into these images. So for example, University Police was inspired by one of the building models in there, same as the wagon wheel, and having something iconic such as our icon for Alfred State. In comparing the cost comparison for our machines to Creative Machines, for our machine is about 180 cubic feet. So for a machine that size created by Creative Machines, the average price would be $140,000, which is a lot more than ours. So I would like to, with that, I think we can give ourselves a little bit of credit for considering how much we've been able to do with about a very fraction of the budget that our inspiration was from. So next we have the demonstration of our lift and machine that we have so far, and any questions if you guys have any. So yeah, thank you guys. Would you like the demonstration first or questions? All right.
So is that just like a tablet or something that's running off?
Yeah, that's just like a stuff.
Oh, okay.
Just for context, we have little stoppers on the tracks since they're not complete, so all of the marbles are kind of stacked up with the little temporary boxes. And once we add in more track, we just move them to the new end of it so we can keep testing without marbles flying all over the place.
And let's keep it variable so we can change the rate of our going to the track as well.
Is there something that's switching which track they go down, or is it just random?
Yeah,